Hey everyone, welcome to my third mobile robotics video. We're going to pick up where we left off again. So we'd left off on cross-sensitivity, and our next bullet point is going to be error. So this is in relation to characteristics of the mobile robot that can't be replicated, might not necessarily be replicated in a real-world environment, as compared to the same characteristics being measured in a lab environment with controlled external variables. So error is just the difference between a mobile robot sensor's measurements, what the mobile robot has actually produced, the sensor has actually produced, and the actual value. So if we have a value that's true and measured, that we know is true, we call that V, and a value measured by the sensor, and we can call that S. Then let me just zoom in, so yeah, I don't want it to be on two separate side-by-side pages. So the error will be equivalent to is equal to M minus S. So it's just the difference between the actual value and the sensor's measured value. And there are two categories of errors. There are systematic errors and random errors. Systematic errors are caused by factors or processes that can be modeled in theory, so they can be predicted. So they're predictable as they're caused by factors that can theoretically be modeled. Right, I'll just continue. Sorry about that. Okay. And then, let me just add the systematic error here. Okay, and again, they're predictable because they're caused by factors that can theoretically be modeled. And then on the other hand, we've got random errors. These ones are not predictable because, as you might guess, we can't really model them, or at least have a sophisticated model for them. And we can't mitigate these errors, also we can't reduce the effect of these errors or reduce the size of these errors with more precise sensor machinery. These can only be described in probabilistic terms. So let's say unpredictable as cannot be modeled. Let's just add sophisticated just in case. So it can't be predicted using a sophisticated model. And also be mitigated with increased sensor precision. only described in probabilistic terms. Okay, and now our next little category is going to be accuracy. And again, this is just another characteristic. So this is the degree to which a sensor's measurement and the true value, the degree to which the sensor's measurement is close to the true value, effectively. So it's a measure of how close the measurement is to the actual value. You can think of it that way. Mobile robot sensors measurement is to the actual value, and we use the error to figure out the accuracy. So the accuracy is equal to 1 minus the error. 1 minus error over v, where v is the real value and error is the error that's been I mean, we work out the error with m minus s. Oh, but let's call this s, since we called the measured value s. So it's the measured value s, the error, and then 1. So we do 1 minus the error, which is the measured value, which is the measured value minus the this is so sorry, this is supposed to be a v. So this is the actual value minus the measured value. That's how we figure out the error, over the measured value. So for instance, if we were to have an actual value of 1.1 and let's say a measured value of 1, then the error would be 0.1, and 0.1 over the measured value, which is 1, would be just 0.1. So the accuracy would be 0.9. That's the degree to which the actual value, the measured value, is similar or conforms to the degree to which the measured value conforms to the actual value. And after this we have precision. Precision and accuracy are sometimes confused. This, the precision itself has nothing to do with accuracy. As in, it has nothing to do with how close the value measured is to the true value. This is entirely based on how close how close consecutive results are to each other. So it's the reproducibility of results. So it measures reproducibility of results. Now the actual equation for this includes the standard deviation of the random error, which I'm not going to be able to type out right now, but I will add this as a link in the bottom of the description, so you can check that out there. Effectively, it's just an equation, and it doesn't need too much explaining. It's to do with the standard deviation and the precision itself is the range over a value where that value is derived from the standard deviation. So yeah, I'll add an explanation of that in the description, since I don't really have the tools to, or at least if I try to sketch this out, it would take way too long. So yeah, and our next category is calibration. So a sensor usually is calibrated before it's used for what is supposed to be reliable measuring. And it plays a significant role in signal conversion. And it involves, it may involve one or more of the following. Finding limits, linearization, right, the American spelling is with a Z. I still haven't fixed the I still haven't fixed my language. It should be English United Kingdom, but oh well, I'll fix it soon. So and also fixing / storing reference points. Okay, and next, after this, we have quite a few other sensors. We're going to have inclinometers next, but I think that's about it for the characteristics that can't be reasonably measured in a laboratory environment, and then have those laboratory results extrapolated to the real world. So next time we will continue with a look at some other sensors. So thank you very much for tuning in, and I hope you enjoyed, and I hope you learnt plenty of new things. See you later.